hybridization of s, p and d orbitals. In the last class, we have done the s and p, and we said that there are sp3 hybridized orbitals. All right. It has sp2 hybrid orbitals, and it has also got sp hybridized orbitals. The rules remaining that the number of atomic orbitals that are undergoing hybridization are same as the number of hybrid orbitals obtained overall. All the hybrid orbitals will form the sigma bond. The atomic orbitals that are taking part in hybridization are of comparable energy, and the hybrid orbitals will assume the direction of the dominating orbitals, meaning if s is merging into p, then the p orbitals, the basic structure of the orbitals will be of the p kind, but though they'll become slightly shorter and fatter due to the inclusive of s character in it. So this was what we were studying about sp3, sp2 and sp. Now you also have to do the d hybridization involving the d orbitals. Now when it comes to the hybridization involving the d orbitals, there are two things to note here. The d orbitals are not present in the second period element. So if an element of the second period is undergoing hybridization involving the d orbitals, then it doesn't, because the d orbitals are not available, so it will not help. But if you are talking about, the third period elements or fourth period elements, then the d orbitals, they start interacting. Those d orbitals which are of comparable energy, they will start interacting also with the s and the p orbitals, and therefore the hybridization including the d orbitals is also called as dsp hybridization. Now again, the how many d orbitals are involved, how many s are involved. I mean, s will always be one. How many p orbitals are involved, how many total number of atomic orbitals are undergoing hybridization, all this together will decide the shape or the geometry of the molecule. But if you look at it closely, sometimes, if it is given as dsp3, all right, or sp3d, does it mean the same? No, it does not mean the same. The inclusion of the d orbitals, whether it is written before the sp hybridization, sp3 hybridization here, or whether it is written after the sp hybridization states, then that is going to tell you about which d orbitals got involved in the hybridization state. Basically, a lot of importance is given to this hybridization state of the including the d orbitals in coordination chemistry. Okay, here also we will be doing some few examples related to the coordination chemistry. I mean, coordination chemistry would mean compounds which contain coordinate bonds, like you have the complex compounds. Okay, so those compounds which are complex salts or which have complex entities, they are the ones usually, which involves the d hybridization of the d orbitals along with s and p. All right. So let us, to understand that, let's go to this, and we will be discussing elements which will be belonging to the third or the higher periods. Okay. Higher periods in the sense where the d orbitals are available. So let us first take the case of dsp2 hybridization. Let us first take the case of dsp2 hybridization. Now, if you look at the molecule, it is having one number of d, one number of s, and two numbers of p orbitals. That means a total of 4 atomic orbitals are getting involved. These 4 atomic orbitals have to be of comparable energy. Only then they will be able to undergo hybridization. Now, you will say that, miss, in that case, even the sp3 hybridization has 4 number of atomic orbitals. Yeah, correct. But in this case, the p numbers are 3 and one s number is there, and these together are forming the 4 atomic orbitals. That is correct. But the shape of this or hybridization, the molecules having this kind of hybridization will have a tetrahedral shape, whereas the molecules that involve the DsP2 kind of hybridization, they have a square planar structure. Okay, why this happens, a lot of calculations and all that will go into it. Right now we will just understand what is happening, how it is happening, why it is happening. That involves a lot of calculations, and more deep studies have to be done for that. Right now we will just learn that when it is sp3 hybridization, like in the case of carbon in methane or carbon in any other alkane compound, the sp3 hybridized state of carbon atom indicates that that carbon atom is going to have a the molecule obtained by that carbon atom is going to have a tetrahedral structure at every carbon atom. But when it comes to dsp2, again 4 number of atomic orbitals are included, but it is going to be a square planar structure. Now, to understand the dsp2 hybridization, one of the best examples that we can actually take up here is the formation of the nickel, all right, Cn, all right, whole 4 2 minus ions, all right. That is a complex ion of nickel, tetracyanonickel ion, nickelate ion. Okay. Naming of the coordinate compounds, the magnetic behavior of the coordinate compounds, the whether it is outer spin, inner spin, I mean, high spin or low spin, outer orbital complex or inner orbital complex. These are the things you will study in detail in standard 12 coordination chemistry. But right now, you will just learn a few examples involving the hybridization of the d orbitals. Now, if I look at this complex entity that has been obtained, this is actually a complex that is formed because you see it has, this is an I here, children. This is a nickel ion, okay, I it will be. It has got 4 cyanide ions which are coordinately linked to, which are linked to the nickel ion by 4 coordinate bonds of the 4 different atoms, groups, that is cyanide group. And overall it is going to carry a 2 negative charge. This bonding that is there is going to be through the nitrogen. Okay, this coordinate bond that is occurring is due to the lone pair of electron that is there on the nitrogen. So the rules for the coordinate bonding is the same, that the one of the ions, one of the atoms in the group attached is going to have a lone pair of electron, which it is going to give towards the central metal atom, that is the nickel ion in this case. So this is the complex entity that we are talking about. Now, what about the hybridization state? If you want to really understand, then you have to know that nickel has an atomic number of 28. Okay. If you write down its electronic configuration, it will go as 1s2, 2s2, 2p6. Then, of course, you have the these written, you have 3s2, okay, then 3p6, okay, then 4s2, that makes it 20, and of course you have the 3d8. This is the electronic configuration of a nickel atom. Now when it enters into, or when it is forming a complex, then it is supposed to convert into a nickel ion. Pay attention. When it is forming nickel ion, it has to lose 2 electrons. From where will it lose the 2 electrons? Is it going to be the 3D or is it going to be the 4s2? It is the 4s2 electrons that will be lost. So what you will get for a nickel ion, though its atomic number is 28, the electrons lost from 4s2, and it will be left with 3p6, 3d8, all right, and 4s0. That is 4s will not have any electrons. Now, if you write down the box diagram for this, if you write down the box diagram, then D is going to have 5. So I will write down the box diagram in blue so that it's easier for you to understand. So this is for the 3D, 1, 2, 3, 4, and 5. and then you have a 4s, and if you have touched the fourth shell, the 4p is also available. All right, so this is 4s, this is 4p, and this is the 3d. Okay, now when it formed the nickel ion, two electrons from the 4s has been lost. So what are the electrons we are left with in the outermost shell now? You have 1, 2, 3, 4, 5. Now the pairing will start. 6, 7, and 8. Okay, so you have two unpaired electrons in the nickel ion. Now, in coordination chemistry, you have to know that these groups which are attached to the central atom here, which are usually the transition metal ions, these groups that are attached, okay, they are either strong or weak, and they are called as ligands. They are called as ligands. Now, these ligands are either they are having a strong field or they are having a weak field. Now, cyanide ion is supposed to be having a strong field. When it has a strong field, whenever these groups have a strong field around them, then what they will do is they will force the pairing of electrons in the orbitals, going against the rules that we know of filling up of the electrons. All right, so it is going to go against the rule where it says, that electrons will first add up first they will occupy singly, and then the pairing will start. All right, so in that case, what rule is that? What rule is that? Anyone? It is going to go against the rule. Which rule? It is going to force it to pair up. All right, why will it force it to pair up? Because of its what you say, the because it has a strong field. And when it is going to force it to pair up against the rule of, that is, maximum multiplicity, Hund's rule, what will it do? It is going to force this electron to enter here. I hope you remember all that, children. So when it is being forced to pair up here, then what will happen? You see, I'm going to the next page now. What will happen is that the 3D orbitals, which are having, oh, the color changes, because my hand touches the color and it changes. So it has 1, 2, 3. In the previous one, you had 4 and 5, and then the pairing was starting 6, 7, and 8. Now here you had 1 electron each. Now this electron is being forced. The electron from here is being forced to come here, and it pairs up. So there is a d orbital which is left here, which is unoccupied, and you have the 4s and you have the 4p. Now you understand one thing, children, when this kind of an electronic configuration, if I go back to the electronic configuration of nickel, we have 4s2, then the 3d. You see, there is overlapping. When is that overlapping possible? When they are of comparable energy. So what will happen is, after the two things have happened till now, when nickel lost 2 electrons, the 4s became 0. So the 4s is empty. All right, you check this. That 4s is empty. Then 4p is available because we have already touched the fourth shell. And in the 3D, what has happened? There are 2 unpaired electrons. Due to the strong the field of the ligand, that is the cyanide ion, it's called as the cyano in the coordination chemistry, it is going to force these unpaired electrons to pair up. So it is going to pair up, and when it pairs up, what happens is that this orbit, this also becomes empty, this one becomes empty, and you have a 4s which is empty, and you have a 4p which is empty, and you have one of the 3ds which is empty. This is the 3d, so this is empty. Now what will happen is, when now the molecule is ready to undergo hybridization, and for hybridization, these will undergo intermixing, and 1, 2, 3, and we are talking about sp2. So This one I'll remove here. Since we are doing sp2, dsp2 we are doing, so only these will undergo hybridization. And when it undergoes hybridization, this becomes dsp2 hybridization, and 4 numbers of hybrid orbitals are obtained. The one I'm drawing are in green are the hybrid orbitals. All right. To these empty 4 hybrid orbitals, nitrogen from the cyanide ions will be, nitrogen from the cyanide ions will be giving its lone pair of electron for bond formation, that is for the complex formation. Carbon cannot give because carbon is, not having a lone pair. But since nitrogen has a lone pair of electrons, it is given for these empty hybrid orbitals, and therefore the structure of the nickel cyanide ion, the complex entity, is formed. Once these cyanide ions have given their electrons, then the 4 numbers of hybrid dsp2 orbitals, they will orient themselves, or they will arrange themselves around the nickel in this way, around the nickel ion in this way, therefore forming a square planar structure. Therefore forming a square planar structure. Now see children, these lines we are drawing. Okay, these lines that we are showing is we are drawing. It is, these lines don't actually exist, but the cyanide ions, they arrange themselves around the nickel ion in this fashion, and overall this is going to have a 2 minus charge. Okay, why? Because the complex that we started off with is having a minus charge. All right, so this is the nickel ion, the nickel cyanide complex ion that we got, and it is carrying a negative charge. Why it is carrying a negative charge? Because the oxidation state of nickel in this compound is 2. Let me go to that also and explain. The compound that you are dealing with is nickel Cn whole 4 and 2 minus. How many electrons did nickel lose in forming this compound? 2 electrons. So the oxidation state of nickel is 2 plus. Nickel is in the 2 plus state. Every cyanide ion has 1 negative charge. So a total of 4 negative charges are there. So 2 negative charges get neutralized by the nickel ion, and 2 negative charges are still left to be neutralized. That will get neutralized by any other positive ion, outside the square bracket. It can be, K2, it can be Fe, it can be, with any other metallic ion with a +2 oxidation state. So overall, then the molecule will become, the molecule of the compound will become neutral. So this is little complexing to understand. I will go through the whole thing one more time. We are discussing the dsp2 hybridization. Now, to explain the dsp2 hybridization, the first one that I'm taking is that of the complex entity of nickel. All right, when it is complexing with the cyanide ions. Now, these kinds of compounds in detail you have to study in the coordinate chemistry, in coordination compounds. Right now, here what you have to understand is how the molecule is or the complex entity is being formed. When nickel is ready to form the compound, it is going to lose 2 electrons. When it is going to lose 2 electrons, this is what I'm talking about. Nickel has an atomic number of 28. This is its electronic configuration. When it forms the nickel ion, the 2 electrons of the 4s2 are lost, and this will be its electronic configuration. And this is the box diagram of the nickel ion. Okay. Now it has to form a complex entity with 4 cyanide ions. So where will the cyanide ions, form? 4 cyanide ions have a choice. They can give 1 to 4s and 1 each to 4p, and then have an sp3 hybridization. But this is not seen in the case of nickel complex. What is seen is that the shape of the nickel, the geometry of the nickel ion is square planar, which is shown by dsp2 hybridized orbitals. All right. And there are other factors also, like this compound is found to be diamagnetic. If it has unpaired electrons, then it should be paramagnetic. So if sp3 hybridization is formed in this case, then it is going to show paramagnetic behavior, but actually it is diamagnetic. Why this happens is because as the cyanide ions approach the nickel metal ion, then it forces the pairing of the unpaired electrons, whereby which one d orbital is made empty. All right. So one of the d orbitals is vacated, and it is not that the electron is lost. Electron is moved to the previous orbital where there is also an unpaired electron, and so it pairs up, giving rise to empty d orbital. Since we are discussing dsp2 hybridization, 4 cyanide ions are there. Which orbitals will undergo hybridization? The d of the 3d, one number of s, that is 4s, and two numbers of 4p, that is, you have two numbers of p, that is, it's going to be 4p, 2p, x, py, anyone you can take, x, y, z. So these four numbers of atomic orbitals will undergo intermixing and give rise to four numbers of dsp2 hybridized orbitals, which we have drawn here. Hybridized means they will all be of equal energy, of equal bond strength, bond length. Once this has been formed, the cyanide ions through the lone pair of electron or nitrogen will form coordinate bonds in these empty orbitals, hybrid orbitals. And the resultant structure of the geometry of the ion of the tetracyanonickelate ion is going to be like this, where I have put the tick just now. That is, the square planar structure will be formed. Okay. Now, one thing is here, why it is having a negative charge, that also I have explained, that cyanide ion carries a negative charge. So 4 cyanide ions means 4 negative charge. Just now we said that nickel is forming a nickel ion of Ni2 plus. That means it is losing 2 electrons. So if it is losing 2 electrons, then with the 2 positive charge, it is neutralizing the 2 negative charge of the cyanide ions. 2 extra negative charge is written out on the bracket outside. This complex entity that is formed, is having a 2 negative charge. And this can be, neutralized by using any di-positive atom, metal atom, or using two numbers of unipositive metal atoms, and the compound can be formed. But in this case, we are focusing mainly on the hybridization state of the nickel, and that is dsp2 hybridized orbital. Now, your question could be that, Miss, can we write it as, is it necessary to write it as dsp2? Can we not write it as sp2d? No, this will not be written. It will be this, dsp2. Why will it be dsp2? Because you see, it is the 3d, that is the inner d orbital, which is being used up. And therefore, it is going to be n minus 1 d orbital is involved, and ns is involved, and two numbers of np2 are involved. So that is why it is, the d is written before s and p. Anywhere in the hybridization state, if you see the d written after the s and p, that means the d orbitals of the valence shell are being used. Okay, let us do an example of that kind. If I am talking about sp3 dehybridization, all right, so in that case we can take the example of, let us say, orbital structure will actually arise PCl5 molecule. In this case, it is not a complex ion, it is just a, covalent compound that is formed, which shows an violation of the octet rule. In there also you had studied. So phosphorus has an atomic number of 15. Electronic configuration is going to be 1s2, 2s2, 2p6, that makes it 10, 3s2, and 3p3. That is px will be 1, 3py will be 1, and 3pz will be 1. Okay, so it is coming to 3px, 3py, and 3pz. This is the electronic configuration you have. If I look at the p orbital, then in this case, you will see that in the excited state, you have studied that the s electrons will unpair. When the s electrons unpair, where will the unpaired electron go? It will go to, if I draw the box diagram, this is S2, this is the P, each containing one electron, and you have the 3D, which is available, but it has not been used so far. So this is 3S, this is 3P, and this is 3D. When the unpairing occurs, this electron from here goes to 3D because we want unpaired electrons. Okay, once it goes here, then the hybridization of these will happen. Hybridization of 3s, one number, 3p, three numbers, and one number of d orbitals will undergo hybridization to result in the formation of 1, 2, 3, 4, and 5. So 1, 2, 3, 4, and 5. And each one of them will get one electron. So these are sp3d orbitals, hybridized orbitals. Now think about it. In this case, the d orbital is of the same kind, is of the same shell. The d orbital is of the same shell, that is 3s, 3p, and 3d. Obviously, d comes after s and p, so it is written like this: sp3d orbitals. Total number of 5 hybrid orbitals we are getting. And you have a chart given in your book. You will find it. It is given. You can just learn it up from there. That when the hybridization is sp3d type, then the structure is a trigonal bipyramidal structure. Structure is a trigonal bipyramidal structure. All right. All these are Cl. One Cl, one Cl. This is Cl. This is Cl, and this is Cl. Actually, it is shown like this. There are 3 which are on the same plane. This one, and this chlorine. These 3 chlorines are on the same plane, whereas the encircled ones are, away from the chlorine a little bit, and it is further away. So when PCl5 reacts, it is these 2 Cl which are given out first. Okay, then the PCl3 will be formed, and then if further reaction occurs, then the Cl will be involved. So you have the axial and the planar here. Now one question here. Why is it that NCl5 is not formed, but PCl5 is formed very often? Because the second period elements do not have empty d orbitals, and therefore when it unpairs, it cannot go to the unpaired electrons. Followed? And that is why the structure is to be understood like this. Okay. Now, when it is having a trigonal bipyramidal structure, it means that you have 2 triangles, basically attached through the plane. Okay, through the triangular plane. And that is the structure of the compound. These are slightly longer. These are slightly longer. The difference in the bond length of the 2 is because, the axial bonds, they suffer more repulsion. All right, then the ones which are on the equatorial, that is on the planar, that is the equatorial bond pairs. All right, the 3 phosphorus and chlorine equatorial bonds, these are called as the equatorial bonds. Okay, these phosphorus is in the middle. They are called as the equatorial bonds. All right, they are repelled only by the PCl axial bonds, whereas a larger repulsion is experienced by the PCl equatorial bond pairs increases. Actually, just remember that this bond length is more compared to these bond lengths because these axial, these are called as the axial, and these are called as the planar or the equatorial. These are having less repulsion as compared to the chlorines which are attached on the equatorial plane, sorry, along the axis. So what I would suggest is that you can always open the book and you can try out more examples that show such kind of bonding. If you talk about D2sp3, that means two numbers of D n minus 1 D are involved, and sp3 hybridization is there, which means a total of 6 hybrid orbitals are obtained. If you talk about sp3d2, that means also that 6 orbitals are involved, but in the case of sp3d2, the d orbitals are from the same shell, from the same outer shell. So number of examples are given, the chart is given, just learn it up. Okay. When it comes to coordination compounds in standard 12, you will be doing a little bit more in detail about this. All right. When it comes to sp3d2 structure, then the shape or the geometry is kind of octahedral. And when it has 7 bonds, that is sp3d3, then it has a pentagonal bipyramidal structure. Compounds of these kinds are both important. What are those compounds which you would specifically, I would say that you go through that. That is IF7. I think it is IF7. Yeah, IF7 and xenon hexafluoride. Xenon, it's not writing. Xenon hexafluoride. These are the two which have pentagonal bipyramidal structure. The central metal atom is placed here, and you have one here, 1, 2, 3, 4, and 5. All right. And then you have one pointing upwards and one pointing downwards. In the case of xenon, there is a pair of electron also involved. And in the case of iodine also, if you, when you try doing the structures, you will understand. In some structures, you will find that a orbital with a pair of electron is shown. This means that that pair of electron, that lone pair of electron is directed along that direction. All right. So now the last part about this hybridization is how would you predict the hybridized state of an atom in a covalent or an ionic species? See, all the time it is not very accurately possible, but more or less by this method you can find out the hybridized state and you can find out the shape. If you know the hybridization, you will be able to find out the shape of the molecule also. So the formula given is, it's given in your book, so don't worry. I is equal to Ga. We are going to predict the hybridization state of the atom in a molecule. Okay. Half VE minus V minus C. This is given in your book. I'm just explaining. You go through it, you will understand. Ga stands for the groups attached. This stands for the valence electrons. This stands for the valency, and C stands for the charge. The value of I will tell you what kind of hybridized state the central metal atom is in. Okay, let us take the example of SO2. And we want to find out the hybridized state of, let us say, sulfur. So you apply, what will I equal to for sulfur? I is equal to, how many groups are attached? 2 groups are attached. Groups or atoms, anything it can be. Plus half you write, because it's there in the formula. Then valence number of electrons. Now which electrons where? Where do you count the electrons? Electrons on the sulfur atom, the atom for which we are finding out the hybridized state. So the number of valence electron on sulfur is 6, belongs to the oxygen family. sulfur in this atom? How do you find out the valency of sulfur in this atom? We know that the valency of oxygen under all conditions is going to be 2 here, unless it's forming a peroxide linkage. So it's going to be 2, and there are 2 oxygen atoms. So the sulfur is actually showing a valency of 4. So you will write 4. Is the charge being carried by the sulfur dioxide molecule? No. So this one will be 0. Now you calculate. You have 2 plus half. 6 minus 4 is 2, minus 0 is 2. So it will be 2. So this is actually going to become equal to 3. So the I is equal to 3. All right. Once I have the value of I, we can actually find out the hybridized state. Okay. How can I find out? There is a chart again given in your book. You can look at that. If the value of I is 2, then it is sp hybridized. If the value is 3, if the value of I is 3, then it is sp2 hybridized. If the value of I is 4, then it is sp3 hybridized. Now you can say that it can also be dsp2, but again, as I said, that this is just predicting. Okay, so then in that case you will have to go into the the formation, what kind of molecule is involved, formation of that molecule, and accordingly it can be decided. Then if the value of I is 5, that means it is sp3d, and so on it goes. So if the value is 6, then it is sp3d2. sp3d2. You see, actually it is corresponding to the number of hybrid orbitals that are obtained. So I is actually giving us the number of hybrid orbitals that will be obtained. And so if the number of hybrid orbitals obtained are 2, then it is undergoing sp hybridization, and if it is 3, it is undergoing sp2 hybridization, and so on. Okay, so this is about the prediction of the or you can say prediction of the state of hybridization of the central metal ion. We can take one more example of a charged ion. Charged ion, we can take the case of, let us say, we did SO2, no? Okay, let's take the case of most commonly known NH4 plus. Okay, we have to find out the value of I. Number of groups attached in this case is 4 plus, applying the formula, half. All right. How many valence electron does nitrogen have? 5. Valence electron is 5. Okay. Then what is the valency shown by nitrogen here? Valency shown is 4. Normally its valency is 3, but here it is showing a valency of 4 because 4 hydrogens are there. So 4. And what is the charge carried by the ion? NH4 plus is having a 1 positive charge. So you have to subtract and then write the charge, that is 1, and then you close the bracket. So this one will equal to 4 plus half, okay, 4 plus half, within brackets it's going to be 5 minus 4 is 1, minus plus is minus, so it's going to become equal to 0, and therefore overall it is going to become equal to 4. So what did we just do? That if the nitrogen is having I value is 4, that means it is going to show sp3 hybridization. So it is showing sp3 hybridization. All right, you can check the chart also we just did. See this, where is it? Here. You see 4, it is sp3. Okay, so this is how you have to study about the hybridization of the different okay, you have to find out the hybridized state of the different metal or the central metal atoms or non-metal atoms, whatever, to find out this. So now this kind of completes your hybridization. The next very important topic that we have to do again, why I'm saying very important is because invariably you will get a question from that, undoubtedly. That is the molecular orbital theory. Okay. Now, in the molecular orbital theory, again, it's not a very small topic. So let me see, should I do it today or should we do it tomorrow? Tell me, children. Do you have any class lined up just now? Yes, children, you all need to respond.
No, miss.
No stands for no class. Or you want to do it
No
tomorrow?
classes are there.
Hmm? Tell me, be honest.
Tomorrow.
Tomorrow. Okay, even I feel so. All right, then tomorrow again we are connecting at 2:30, and I'm sorry I goofed up the timings today. No, I made it 9 and so many started connecting. So okay, tomorrow, but be prepared for a little longer class than what we have done today. Tomorrow I will complete the entire molecular orbital theory, and in fact I would like to complete the entire chapter tomorrow. Okay. So enough for today.
Thank you, miss.
Thank you.
Thank you, miss.